This is the second part of the chapter, and in this chapter we'll do combinations, and we did permutations already. So at the bottom of this page, you want to highlight: a permutation is an arrangement of elements in which the order of the arrangement is taken into account. So that's what we've already done with people standing in a line and us taking a picture of them. It would be different if Abby sat in the front and we took the picture, or if Cameron sat in the front and we took the picture. Combination is a selection of elements in which the order of the selection is not taken into account. So it doesn't matter who goes to Hawaii, just that all of you have a plane ticket. Over the page. Okay, so some examples with this to think about. 5 students, Al, Byron, Cullen, Dave, and Eric, take part in a cross-country race to represent their school. Suppose the winner of the race wins $50, the runner-up wins $25, and the third place runner wins $10. So this right here is a permutation. It matters what order they place in. So the table shows all the possible ways in which the 3 prizes could be awarded to the 5 participants in the race. A stands for Al, B stands for Byron, C for Colin, D for Dave, E for Eric. And then you could go through and you could make up this whole long list, but good heavens, it's exhausting, and so we don't want to do that every time. So, as it says, is this an example of permutations or combinations? Well, we know it's a permutation because order matters. And how many ways are there to award the 3 prizes? Well, we know we've got 5 people, and if we do 5 people and we permute 3, or we select 3 of them, or pick 3 of them and arrange them, then that will give us the total number of ways there are. So if we do that on a calculator, then we get 60. B part, for participants in the cross-country race, the school has been awarded 3 places at a running clinic. The school coach decides to select the 3 lucky students from the ones who took part in the cross-country race. So again, you're using the exact same people, but now it's just a matter of taking 3 of them. We don't care who gets chosen first or last, just so that you get chosen and that you get to go to the running clinic. So in this case, this is an example of a combination where order doesn't matter, just so you get to go. And in this, you will do 5, choose 3. So the C stands for choose, and you find it in the same location as you did the permute button. In fact, you probably saw it. So we're going to do 5 math, slide over to probability, and down to, 5 math, slide over to probability, and down to number 3, the choose. So 5, choose, 3, enter, and we get 10. So a big difference when order doesn't matter. There's a lot less options. So next page. When should we use choose? And they give you an equation for choose here that we'll think about. It's also on our formula sheet. So it'll be n factorial over n minus r, whatever those 2 numbers are, factorial, and then an r factorial. So you'll see that if we do questions that involve using the algebra to that. So when should we use choose? Anytime the order doesn't matter, so committees are often. Examples of when we should use choose. If you're making a fruit salad and you're selecting items to go in the salad, because it's just all going to get mixed together. Pizza, all going to get mixed together. The order you choose the toppings doesn't matter, just so long as they're on there. And things like that. You'll come across ones and you'll realize that those are choose instead. That's the hardest part of this, is deciding whether it is a choose or a permute. So let's do some examples with this now. And we have number 1. 3 students from a class of 10 are to be chosen to go on a school trip. So we've got 10 total, and we're going to get 3 of them. In how many ways can they be selected? And write the answer in factorial notation and evaluate. Well, we can do that in factorial notation, I guess. So we want 10, choose 3 of them to go on the trip. And let's just put it into the formula part, is what they're saying from up above. So if we look at our formula, and now in it goes. So 10 is in the end spot, 10 factorial over 10 minus 3 in brackets, factorial, and 3 factorial. So that's 10 factorial over 7 factorial, 3 factorial. And we could put it on our calculator at this point and get 120, which really then, why didn't we put it on our calculator at the very beginning? So really, I guess we're going to confirm that using the and choose our key, but certainly we are going to do that most of the time with our choose button. So 10 choose 3 is 120. Okay, here's a good one. To win the Lotto 649, a person must correctly select 6 numbers between 1 to 49. Jasper selected the 6 numbers from the birth dates of his family: 3, 7, 9, 11, 20, 29. How many different selections of numbers could he have made? So if we think he's got 49 numbers total, because it's not 0 to 49, it's 1 up to 49. So 49 total, and he's going to select 6 of them. In Lotto 49, and I guess everybody knows this but me, anyways, the order doesn't matter. It's just how many you get right. I didn't know that, but anyways, I guess there's enough ways that you could lose that they're not too worried. So if we do 49 choose 6, and let's see, and it's going to be a big number, because otherwise they'd be giving away a lot of money all the time. So 49 choose 6. Not random norm. 49 choose 6. Oh yeah. One, 3, 9, 8. 3, 8, 1, 6. Almost 14 million ways. So if you buy one ticket, you've got a 1 in 14 million chance of winning. And this is why you don't buy lottery tickets, because you will not win. That's what the math says. Okay, number 3. The Athletic Council decides to form a subcommittee of 7 council members to look at how funds raised should be spent on sports activities in the school. There are a total of 15 council members, 9 male and 6 female. The subcommittee must consist of exactly 3 female. Determine the number of ways of selecting the females. So we start with, we've got 15 total. They're comprised of 9 and 6. We need 7 total, comprised of exactly 3 female. So if I have 3 females that I need to select out of the 6 that are in the Athletic Council to begin with, then I'm just going to think 6 choose 3. And that gives me, on my calculator, 20. And the males, so I've got 9 males total. I'm going to need 4, because otherwise I don't have my committee of 7. So 9 choose 4 is going to be 126. They're not going to lead you through this all the time. That was just for this one. So really the subcommittee, what you're going to think is this idea here. You need 4 of them coming from the 9 that are there to begin with, and 3 of the females coming from the original group of females that there were. So they're going to have you put this together. This is and, so you need males and females, which means you'll times them together. So really you would write 6 choose 3 for your females. And I guess if we did it in order like we've got there, it doesn't matter because you're going to times them together. But we'll put it in this order so it looks the same. So we've got 9 choose 4 for males and 6 choose 3 for females. And then we can type that all into our calculator at once. And when we do that, we just have to be careful, as usual, that we're not pressing extra buttons or wrong ones. So 9 choose 4 times 6 probability choose 3 equals 2,520. And that would be the number of different committees that could be made using exactly 3 females. And B part now. In how many ways can the subcommittee be selected if Bruce, the football coach, must be included? And this is similar to last chapter or last section when we decided, okay, if we've got Bruce, that's one way of getting Bruce, which means we've already got 1 of the males, so we just need 3 males and 3 females now. Out of our original, we won't have 9 anymore. We would have 8 males to take that out of, and we would still have the 6 females from there. So now we'll get the males. We've got 8 of them. We're going to choose 3 times 6 females. We're going to choose 3. And that equals, and now this should be a smaller number. So 8 choose 3 times 6 choose 3 equals 1,120, which is what we expected, something smaller. Okay, last example page. Deck of cards. This is a good one. Usually, deck of cards are combinations, so usually they're the choose. Here we go. A standard deck of 52 has the following characteristics. 4 suits, so spades, clubs, diamonds, and hearts. So spades, and those are black, and clubs, which kind of look like a 3-leaf clover, and those are black, and diamonds that are red, and hearts that are red. So 4 suits, each suit has 13 cards. 2 suits are black, the spades and the clubs, and 2 suits are red, the diamonds and the hearts. Face cards are considered to be Jack, Queen, and King, not Ace. Ace is not a face. It just rhymes. Ace can be counted as a high card or a low card depending on the game that they're having you play, but they will have to tell you that every time and you don't have to remember. So A part, how many different 5-card poker hands are possible? So we think we've got 52 cards total. We're going to choose 5 of those. And it doesn't matter what order we're dealt them because we're going to take them in our hand and then we're going to sort them and organize them and hold them so that we can take a look. So order isn't important. And now this is going to be a big number. Choose 5. Oh, yep. Here we go. 2, 5, 9, 8, 9, 6, 0. Lots of ways. In how many hands will there be all diamonds? So you're thinking, for sure I'm going to have a diamond, which means I'm going to put all the diamonds in a little pile. Well, there's 13 diamonds. So 13 diamonds, choose 5 of those diamonds. And I'll just write the answer instead of us putting it on the calculator. And that will give us 1,287. Okay, part 2. 4 black cards and 1 red card. So 4 black and 1 red. Anytime we say and, we know we're going to times. So 4 black, I'm going to put all the blacks in a little pile. I've got 26 black cards, and I'm going to choose 4 of them, times reds. I've got 26 reds, and I'm going to choose 1 of those. And I'll times it together on my calculator, and I end up getting 388,700. Okay, what about 3 kings and 2 queens? Okay, so we're going to put the kings in a pile, 4 of them, and we're going to choose 3 of them. And times queens in a pile, so there's 4 of them, and we're going to choose 2 of them. This way it ensures we always get what we want. When we put that on our calculator, 24 total. Part 4, 3 kings. So I'm going to be thinking I need 3 kings, but also I need 2 cards that aren't kings so that I have a full 5-card hand that we were supposed to have at the beginning. So 3 kings, I'm going to put the kings in a pile, 4 kings in the pile, and then I'm going to choose 3 of them. 2 not kings. Well, 52, take away 4 is going to be 48. Choose, and now I just need 2 of those. And I'm going to get 4,512. Okay, what about 4 aces? 4 aces means I will need 1 that's not an ace also. So I'm going to put all the aces in a pile, 4 of them. I'm going to choose all of them. 4 choose 4 times, and now all the cards that aren't aces, that will be 48. Choose 1 equals 48. Because there's only one way of getting all of the aces, you just have to pick all of them. Okay, last part, part 6. Oh, we haven't had that up enough, sorry. Part 6. 5 cards of the same suit, called a flush. So we need either 5 diamonds, 5 hearts, 5 clubs, 5 spades, and I need to choose that to begin with. What am I going to decide on for being my suit? So you're going to choose the suit first. And you've got 4 suits. I'm going to choose 1 of them. And now I've got 13 cards in that suit, and I need 5 that are the same. And that ends up being 5,148. These are tricky to piece apart. You have to think of ensuring that regardless of what you pick out of the little pile you've made, it will be what you want. And that's how you'll be able to more easily decide on the parts of these questions. So we are doing all of them except for 9 and 10. So good luck. Do some check, do some check, do some check. Use the answer key if you need to, and try to think like the book. Talk to you later.